A telescope 1 million miles from Earth just looked back 13 billion years and found stars that should not exist yet. We built our entire picture of the universe on maps. Maps of distances, maps of ages, maps of how stars are born and die. Webb is breaking them, one image at a time. We'll go from shattered distance rulers to galaxies older than our models allow, to black holes that grew too fast for physics to explain. If you enjoy the journey, subscribe and stay close, because this one goes deep. Ready? We begin. Step outside on a clear night and look up. Every single point of light you see has a number attached to it, a distance, an age, a position so precise that astronomers can predict where it will be 1,000 years from now. That web of measured, catalogued, trusted positions is what we call a star map. And for centuries, it has been the closest thing science has to a perfect foundation. The first serious star maps were built without telescopes. Ancient Greek astronomers catalogued around 850 stars by naked eye alone, placing each one by its angle from the horizon and its position relative to others. They were accurate enough that sailors crossed oceans using them. Armies timed their wars by them. Entire civilizations built calendars, religions, and identities around the patterns those maps revealed. Then the telescope arrived. Suddenly, the sky exploded. Thousands of stars became millions, and the question changed from where are they to how far away are they? That second question turned out to be one of the hardest problems in all of science. You cannot walk a tape measure across space. You cannot bounce a signal off a distant star and wait for the echo. Distances in space have to be calculated through layers of logic, each one built on the last. Astronomers call this the cosmic distance ladder. The bottom rungs use geometry. If you observe a nearby star in January, and then again in June, Earth has moved about 186 million miles around its orbit. That shift creates a tiny angle, and from that angle you can calculate the star's distance exactly the way a surveyor triangulates across a valley. This method works reliably out to a few thousand light years. But most of the universe sits far beyond that range. So astronomers climb to the next rung, standard candles. A standard candle is any object whose true brightness scientists already know. If you know how bright something actually is, and you measure how dim it looks from here, the math gives you the distance. The dimmer it looks, the farther it is. Simple, reliable, and the backbone of modern cosmology. For most of the 20th century, the most trusted standard candle was a type of star that pulses. It swells and shrinks in a steady rhythm, brightening and dimming like a slow heartbeat. Astronomers discovered that the speed of that pulse directly tells you the star's true brightness. Measure the pulse, know the brightness, calculate the distance. These stars became the measuring sticks humanity used to map the entire observable universe. Every galaxy distance we have, every estimate of how fast the universe is expanding, every calculation of how old the cosmos is, all of it traces back, rung by rung, to those pulsing stars, and the assumption that we understand them correctly. For 100 years, that assumption held. The maps grew more detailed, more precise, more trusted. Scientists built entire models of cosmic history on top of them. They described the universe's birth, its expansion, its future fate, all derived from a chain of measurements stretching back to the behavior of those rhythmically beating stars. And then James Webb launched. It did not immediately cause alarm. The first images were breathtaking, celebrated, shared across every screen on Earth. Scientists cheered. Governments praised the achievement. But in the data, quietly, something was wrong. The stars were not behaving the way the maps said they should. And if the stars were wrong, everything built above them on that ladder was wrong too. The question was, how wrong? And the answer, when it came, was uncomfortable enough to keep entire research teams awake at night. What Webb actually saw in those first critical observations, and why it sent a shiver through the astronomy community, is where this story truly begins. James Webb sees the universe in a way no instrument in human history ever has. To understand why its findings are so disruptive, you first need to understand exactly what makes it different. Because the difference is not just about being bigger or more powerful. It is about seeing an entirely different kind of light. Every telescope you have ever heard of, From the simple refractors Galileo pointed at the sky to the Hubble Space Telescope floating in orbit, was built primarily to capture visible light, the light your eyes detect, the warm colors of a nebula, the pale glow of a distant galaxy. Visible light is the language astronomers have spoken for 4 centuries. Webb speaks a different language. It was engineered to detect infrared light, which is heat radiation, the kind of light your body emits right now, invisible to your eyes, but carrying enormous amounts of information. Infrared passes through dust clouds that block visible light completely. It reveals objects hidden inside stellar nurseries. And critically, it captures light from the most distant ancient objects in the universe. Objects so far away that their light has been stretched by cosmic expansion into the infrared range during its billions of years of travel. Imagine throwing a ball across a room while the room itself is stretching. By the time the ball arrives, it has slowed, spread out, changed. Light does the same thing across cosmic distances. The most ancient light in the universe left its source as visible or ultraviolet radiation, but by the time it reaches us after 13+ billion years of travel through an expanding universe, it has been stretched all the way into infrared. Hubble could barely see it. Webb was built specifically to catch it. To do that, Webb had to solve an engineering problem that sounds almost absurd. Infrared detectors are extremely sensitive to heat. Any warmth near the telescope, even the faint heat of sunlight, would blind them completely. So Webb carries a sunshield the size of a tennis court, folded origami style for launch, and deployed in space, keeping the telescope permanently in shadow. Its instruments operate at temperatures colder than the surface of Pluto. Its mirror is also in a different category entirely. Webb's primary mirror stretches 18 feet across, assembled from 18 hexagonal gold-coated segments that unfolded after launch like a mechanical flower. Gold reflects infrared light more efficiently than any other material. Each segment was polished to a precision measured in nanometers, a scale so small that a human hair crossing it would look like a mountain range. The result is a machine that can detect the heat signature of a bumblebee at the distance of the moon. Scientists mean that almost literally. Its sensitivity borders on the surreal, and when they pointed it at regions of the sky that Hubble could see only as faint smudges, Webb returned images packed with thousands of individual galaxies. Ancient ones, fully formed ones that, according to every model astronomers had built, had absolutely no business looking the way they looked at the age they were at. Hubble gave us a glimpse of the early universe. Webb gave us a close-up, and close-ups have a way of showing you exactly what was wrong with the version of events you thought you knew. The first sign of trouble appeared almost immediately. It was subtle at first, hidden in the light curves of stars in a galaxy 60 million light-years away. A small discrepancy. The kind of thing that gets a footnote in a paper. Except this footnote changed everything, and what it uncovered in that one nearby galaxy pointed directly toward a fracture running through every star map ever made. The alarm did not sound with a bang. It arrived as a number that refused to cooperate. In Webb's first operational months, a team of astronomers pointed it at a galaxy called NGC 4258. This galaxy sits about 23 million light-years from Earth, close enough on cosmic scales to study in fine detail, and scientists have been using it as a calibration anchor for decades. It contained pulsing stars, the rhythmically beating standard candles that sit at the heart of the cosmic distance ladder. The team wanted Webb to measure those stars more precisely than Hubble ever could, expecting the result to confirm what they already believed. Webb confirmed something different. The pulsing stars in that galaxy were blending together in Hubble's older images. Webb's sharper infrared vision revealed that what Hubble had been reading as single clean pulses were actually multiple overlapping stars crowded into dense regions, their individual signals mixing into one combined glow. Hubble had not been able to separate them, so for decades, astronomers have been measuring a blended average brightness, feeding it into their distance calculations, and trusting the result completely. Picture trying to measure the brightness of a single candle in a room, but you cannot see clearly enough to tell that 2 candles are sitting right next to each other. You measure what looks like one bright candle, record the number, and build your calculations on it. Every distance you derive from that measurement carries the error forward invisibly. That is what had been happening, confirmed now in hard data. Webb's resolution was sharp enough to separate the individual stars, and when astronomers did that separation, the distances shifted. Some measurements moved by enough to matter. And in cosmology, small shifts in foundational numbers send shockwaves through everything above them. The team published. The astronomy community paid close attention. Some researchers were skeptical, urging caution before drawing large conclusions from early Webb data. Others immediately grasped the implication. If the nearest, best-studied pulsing stars showed this kind of contamination in Hubble data, then every galaxy farther out, measured with even less resolution, carried the same or larger errors. The cosmic distance ladder had always been built with careful checks, but those checks had been performed with Hubble-grade vision. Webb-grade vision was a different instrument entirely, and it was now finding that the foundations were less solid than assumed. There was a detail in the data that made things even more unsettling. The shift in the measurements did not randomly scatter up and down. The errors were not chaotic. They leaned in a consistent direction, meaning the distances had been systematically underestimated in a way that would make the universe appear to be expanding faster than it actually is. The expansion rate of the universe is one of the most fundamental numbers in all of science. It tells us how old the universe is, how large it is, and how it will end. That number is called the Hubble constant, and for years astronomers had been arguing about two different measurements of it that refused to match each other. They called that disagreement the Hubble tension. Webb had been sent up, partly to solve it. Instead, Webb cracked the ladder, holding the whole debate together. And that crack, once seen, opened into something far deeper than a measurement error. It pointed toward a possibility that researchers have been quietly discussing in conference hallways and late-night emails for years, that the universe might be structured differently than every map we have ever drawn suggests. What the Hubble tension actually means, why it existed before Webb arrived, and why Webb made it stranger, comes next. The universe has an age. Scientists calculated it as 13.8 billion years, a number derived from multiple independent measurements that all converged on the same answer. It felt settled, firm, the kind of number you engrave on the foundation of your entire cosmological model. Then, Webb started sending back images of the early universe, and some of the galaxies in those images looked like they had been around far longer than 13.8 billion years should allow. Here is the problem in plain terms. When we look at distant objects, we are looking back in time. Light takes time to travel. The light from a galaxy 10 billion light-years away left that galaxy 10 billion years ago, so we see it as it was 10 billion years ago. Webb can see galaxies so far away that their light left them when the universe was only a few 100 million years old, a cosmic infant. When you see an infant, you expect infant features, small, simple, still taking shape. Astronomers expected the earliest galaxies to look like that, irregular, chaotic, just beginning to accumulate mass and form stars. The models said that was the only physically reasonable expectation. Gravity needed time to pull matter together. Stars needed time to ignite and live and die and seed future generations. Building a massive, structured galaxy takes billions of years of that process stacking up. Webb looked at galaxies from that infant period and found some of them fully grown. These were massive galaxies, structured, bright, containing billions of stars already burning steadily. Some had morphologies, meaning shapes and features, that astronomers associate with mature, stable systems. They looked like the kind of galaxy that should take 5 or 6 billion years to build, sitting in a universe only a few 100 million years old. One research team described their data as causing genuine discomfort. A scientist involved in the analysis said, using her own words in a widely reported quote, that these galaxies were simply too big, too early, and that she had no explanation for them. The reaction across the field was not uniform panic, but a shared, serious acknowledgement that something in the standard model of galaxy formation was under real pressure. The standard model, called lambda CDM by cosmologists, describes how the universe evolved from a near-uniform hot fog of particles after the Big Bang into the structured web of galaxies we see today. It relies on dark matter, dark energy, and a set of assumptions about how quickly matter clumps together under gravity. The model works extraordinarily well across most of cosmic history. But in the earliest epoch, Webb can now see the model appears to be producing galaxies too slowly. The universe Webb observes in its infancy looks more evolved, more structured, more productive than the equations say it should be. One possible explanation, still theoretical, is that star formation in the early universe was dramatically more efficient than any model predicts. Early galaxies may have converted gas into stars at a rate 10 times higher than anything we observe in the nearby universe today. Another explanation, darker and more destabilizing, is that the age of the universe is wrong. And a third possibility, the one that keeps cosmologists awake at a specific frequency of unease, is that the physics governing how matter clumps together under dark matter's influence needs to be revised at a fundamental level. None of those explanations are comfortable. All three remain open, and each one connects back to a tension in the data that predates Webb by years. A disagreement so stubborn that scientists named it like a medical condition. That disagreement is where we go next. Two completely independent methods of measuring how fast the universe expands keep producing two completely different answers. That disagreement has a name, the Hubble tension. And despite years of effort, the best instruments ever built have been unable to resolve it. To understand why it matters so deeply, you need to understand what the expansion rate actually tells us. After the Big Bang, everything in the universe was compressed into an unimaginably hot, dense state. Then it expanded. It has been expanding ever since. The rate of that expansion is not a constant speed the way a car moves down a highway. It changes over time, influenced by the gravity of all the matter in the universe trying to slow things down, and by dark energy, a mysterious pressure embedded in space itself that accelerates expansion. The balance between those two forces across all of cosmic time determines the universe's age, its size, and its ultimate fate. Measuring the expansion rate precisely is one of the most important goals in all of cosmology. Astronomers have two primary ways of doing it, and they get two primary answers. The first method looks outward into the nearby universe. Scientists measure the distances to pulsing stars in nearby galaxies, then measure how fast those galaxies are moving away from us. From those two numbers, they derive the expansion rate directly. This method has been refined for decades, and its answer, confirmed repeatedly through careful observation, says the universe is expanding at a rate of around 73 kilometers per second per megaparsec. Do not worry about the units. The important thing is the number. The second method looks backward at the oldest light in the universe. Shortly after the Big Bang, the hot fog of the early universe released a burst of radiation that still fills all of space today, faintly in every direction. Scientists have mapped this ancient light in extraordinary detail, measuring the tiny temperature ripples within it. Those ripples encode information about the early universe's density, composition, and behavior. When physicists run the math forward from those early conditions using the standard model, they predict an expansion rate of around 67. Same units, different number. 73 versus 67. Those numbers sound close. They are separated by less than 10%. But in cosmology, a 10% disagreement in a foundational constant is enormous. Both measurements carry error bars small enough that the two values have essentially zero chance of overlapping by accident. They are genuinely, stubbornly different results from the same universe. Astronomers have checked both methods exhaustively. They have looked for instrument errors, systematic biases, overlooked corrections, anything that would allow one number to slide toward the other. The tension has only gotten sharper with time, as measurements have grown more precise. Each improvement makes the disagreement more vivid. There is a third possibility that researchers discuss with increasing seriousness. Both measurements are correct, and the standard model is wrong. If the physics we use to interpret either the nearby universe or the ancient light contains an error, then the tension is not a measurement problem. It is a physics problem. Webb entered this debate as the most powerful tool ever aimed at the heart of it. Its job was to cross-check the nearby distance measurements with greater precision than Hubble could achieve. What Webb found in those pulsing stars, and what it now means for both sides of the tension, rewrote the terms of the entire argument, and the rewriting was messy, satisfyingly, disturbingly messy. The plan was clean, elegant even. Hubble had measured the pulsing standard candle stars in nearby galaxies and produced an expansion rate of 73. The cosmic background radiation produced 67, Someone, the reasoning went, had made a measurement error, point Webb at the pulsing stars, get sharper measurements, find the mistake, close the gap. Case solved. Field moves on. The Hubble tension was supposed to be a calibration problem, a known instrument limitation corrected by a better instrument. Webb confirmed it was something stranger. When the first careful Webb measurements of pulsing stars came back, they did shift the numbers slightly. The crowding effect Webb revealed, the overlapping signals that had contaminated Hubble data for decades, did push the nearby expansion rate measurement downward by a small but meaningful amount. That was the expected result. That was supposed to be the resolution. Except the shift was not large enough. Even after correcting for the crowding contamination Webb identified, the nearby measurement of the expansion rate remained significantly higher than the early universe measurement. The gap narrowed a little. The tension did not disappear. Scientists published those results carefully, emphasizing what the data showed and what it did not show. What it did not show was a solution. A team led by astronomer Adam Rees, who had previously won a Nobel Prize for discovering that the expansion of the universe is accelerating, published an analysis concluding that Webb's measurements actually strengthened the case for the tension being real. Their reading of the corrected data said the crowding effect explained a portion of the discrepancy, a real and measurable portion, but left a core disagreement intact that pure measurement error could no longer account for. What that means, stated plainly, is that the remaining tension likely reflects something real about the universe's behavior, a gap between what the early universe delivers that our current physics cannot bridge. Some researchers pushed back. They argued that additional corrections might close the gap, that Webb's data contains its own uncertainties, that declaring a physics crisis is premature. That debate is ongoing and legitimate, but the general direction of the field shifted. Before Webb, optimists believed a simple calibration fix would resolve the tension. After Webb's first round of measurements, that optimism became harder to sustain. The problem got more complex, more layered, more interesting in the way that only genuinely difficult scientific problems are interesting. And then Webb did something nobody had planned on. While the tension debate was absorbing attention, other Webb observations were stacking up in the background. Images of the early universe, of the first galaxies, of ancient star populations, data that did not address the Hubble tension directly, but attacked the foundation from a different angle entirely. Because a calibration problem affects your ruler. But Webb was not just finding a bad ruler. It was finding rooms that should not exist, built before the house was old enough to have a foundation. The next piece of this picture is the specific tool that the entire cosmic distance ladder rests on, a type of star so well studied, so trusted, so central to everything we think we know about distances across the universe, that finding a flaw in our understanding of it shakes every measurement made for the last century. In the year 1912, a woman named Henrietta Swan Leavitt changed astronomy forever from a desk at the Harvard Observatory, where she was paid 25 cents an hour to study photographic plates. She was cataloging stars in a region of the sky called the Small Magellanic Cloud, a satellite galaxy close enough to our own that all the stars within it sit at roughly the same distance from Earth. As she catalogued their brightness, she noticed something. Certain stars were pulsing, brightening, and dimming in a steady cycle, and the ones that pulsed more slowly were also intrinsically brighter. The period of the pulse and the true brightness of the star were directly linked. That relationship, called the period luminosity relation, became one of the most powerful tools in all of science. Here is why it matters so much. If you find a pulsing star anywhere in the universe, you measure how long its pulse takes. That period tells you exactly how bright the star truly is. Then you measure how bright it appears from Earth. Divide the true brightness by the apparent brightness, apply the inverse square law, and you have the distance. You do not need to be close to the star. You do not need any other information. The pulse is the decoder. These pulsing stars are called Cepheid variables, named after the constellation where the first well-studied examples appeared. They range from a few days to a few months per pulse cycle. They are massive, luminous stars, bright enough to see across tens of millions of light years. And because Leavitt's relationship applies universally, every Cepheid you find gives you a direct, clean distance measurement. Astronomers used Cepheids to prove that the fuzzy patches of light called nebulae were actually other galaxies, island universes millions of light years away. That discovery, confirmed by Edwin Hubble using Cepheids in the early 1920s, transformed our entire picture of the cosmos from a single galaxy to a universe containing hundreds of billions of them. Every step of the distance ladder above the Cepheid rung was calibrated using Cepheids. The distances to galaxies hosting Type 1a supernovae, another type of standard candle used for even farther distances, were first established using Cepheids. The galaxy recession velocities used to derive the expansion rate of the universe were paired with distances measured using Cepheids. Remove the Cepheids, and the cosmic distance ladder collapses from its second rung upward. This is why Hubble Space Telescope spent enormous amounts of its observation time on Cepheids. This is why the Hubble Key project, a massive multi-year effort, focused specifically on measuring Cepheids in distant galaxies to pin down the expansion rate. The entire enterprise assumed that Cepheids were clean, reliable, well-understood distance tools. For most of a century they were. The physics of how Cepheids pulse is well modeled. The period-luminosity relationship has been checked from dozens of angles. Generations of astronomers built careers on trusting these stars completely, and those careers produced the most precise star maps in human history. Webb looked at those stars with 10 times Hubble's resolution in the infrared, and something in the measurements did not fit. Not a catastrophic failure, something subtler, and in some ways more unsettling. A systematic shift, a quiet lean in the data that suggested the Cepheids had been producing slightly wrong answers for a very long time, and nobody had the instrument sharp enough to see it until now. What Webb revealed in those pulsing stars, and what it means for every distance measurement built above them, is exactly where the story breaks open. Webb's mirror pointed at galaxies containing Cepheid variables and immediately saw something Hubble had been physically incapable of seeing. The stars were not alone. In Hubble's images, Cepheids in distant galaxies appeared as single clean points of light, pulsing steadily against a dark background. That was the assumption baked into every observation. One star, one signal, one measurement. Webb's infrared resolution sliced through that assumption. Cepheids, it turns out, tend to live in crowded neighborhoods. They are massive, luminous stars, and massive stars form together in clusters and star-forming regions packed tightly with other bright objects. In Hubble's images, those neighbors blurred together with the Cepheid itself into one unresolved blob of light. Astronomers measuring the Cepheids' brightness were actually measuring the combined brightness of the Cepheid plus several unresolved companions. This is the crowding problem, and its consequences are directional. If you measure a star as brighter than it actually is, you conclude it is closer than it actually is. Systematically brighter measurements across hundreds of Cepheids in dozens of galaxies means systematically underestimated distances across the entire calibration sample. And systematically underestimated distances means a systematically overestimated expansion rate. Webb's sharper infrared vision was able to separate the Cepheid from its neighbors in many cases, or to model the contamination carefully enough to correct for it. When researchers applied those corrections, the distances to the calibration galaxies shifted slightly outward. The galaxies were a bit farther than Hubble had measured. And when distances shift outward, the expansion rate derived from them drops. A team published results confirming that the crowding contamination in Hubble data was real, measurable, and accounted for a statistically significant portion of the discrepancy between the two Hubble constant measurements. The community acknowledged the finding as important, but the numbers still did not fully reconcile. The corrected Cepheid distances brought the expansion rate down somewhat, but not all the way to the value the early universe predicts. Something else was contributing to the gap. And then a separate Webb discovery added another layer of complexity. Astronomers examining Cepheids through Webb's infrared filters found that dust along the line of sight was affecting the measurements more than previously modeled. Dust absorbs light and makes stars appear dimmer than they are. Dimmer means the astronomer concludes the star is farther away. Overcorrecting for dust pushes distances outward artificially. Undercorrecting leaves them too short. Hubble worked primarily in visible light, where dust effects are large and difficult to separate from intrinsic stellar color. Webb's infrared penetrates dust far more cleanly, giving a truer view of the star's actual brightness. The dust corrections astronomers have been applying to Hubble's Cepheid measurements, based on the best available models, turned out to be slightly off in ways that compound across large samples. Two separate corrections, both real, both measurable. Together, they account for part of the Hubble tension. Together, they confirm that the Cepheid distance scale carried systematic errors that propagated silently through decades of cosmological measurement. That propagation is the part that should make you pause. A small error at the base of the ladder does not stay small as it climbs. It grows, it multiplies, it reaches the top, and becomes an entirely different number than the one you intended. How a single misread measurement at one rung of the ladder reaches all the way to the universe's estimated age is the thread we follow next. Imagine you are walking a straight path across a desert, 1 mile long, and your compass is off by 3 degrees. After the first 100 feet, you are barely off course. After half a mile, you have drifted noticeably. By the time you reach the end, you are hundreds of feet from your target, and every correction you made along the way used the same flawed starting direction. The final error is enormous. The starting error was tiny. The cosmic distance ladder works exactly this way. Each rung of the ladder is calibrated using the one below it. Geometry gives you distances to nearby stars. Those nearby stars calibrate the Cepheid period luminosity relationship. Cepheids in nearby galaxies calibrate the brightness of type 1a supernova, a different class of standard candle, bright enough to see billions of light years away. Supernova distances calibrate galaxy recession velocities. Galaxy recession velocities produce the expansion rate of the universe. The expansion rate of the universe gives us the universe's age. That chain has 7 or 8 logical steps, and each step multiplies the errors of the step below it. A 1% systematic error in the Cepheid calibration does not become a 1% error in the expansion rate. It compounds through every subsequent rung, potentially arriving at the top as a several percent error in the most fundamental number in cosmology. Webb's discovery of the crowding contamination in Cepheid measurements is a confirmed, published finding. The dust correction refinements Webb enabled are real and documented. Both represent systematic errors in the Cepheid rung of the ladder. Neither error is enormous in isolation, but the fact that both errors leaned in the same direction, both making nearby galaxies appear closer than they are, both inflating the derived expansion rate, means they did not cancel each other out. They added together. And that is before considering errors that might exist in higher rungs. The calibration of Type 1 supernovae as standard candles has its own assumptions. Supernovae are used to measure distances to galaxies billions of light years away, and those measurements assume that supernovae behave consistently across cosmic time, across different galaxy environments, across different stellar populations. If that assumption carries any systematic error, it layers on top of the Cepheid errors rather than correcting for them. Scientists are aware of all of this. The field of cosmological distance measurement has always operated with this vulnerability in mind, which is why so much effort goes into cross-checking measurements using completely independent methods. The whole point of the early universe measurement, using the ancient radiation field rather than pulsing stars, was to provide an independent check that bypasses the distance ladder entirely. The fact that the independent check disagrees with the ladder-based measurement is the Hubble tension. Webb's refinements confirmed that at least some of the ladder-based measurement carried real systematic errors. But the independent check has not moved. It still says 67. The corrected ladder says something closer to 70, perhaps 71. The gap is smaller than it was, but stubbornly present. What lives in that remaining gap is unknown. It could be additional measurement errors yet to be identified. It could be a flaw in the standard model of the early universe. It could be evidence of new physics, something that operates differently in the early universe than in the late one. The answer to that question would change everything. And Webb is looking for it right now, not through the Cepheid ladder, but through something entirely different. Something Webb found in the early universe that nobody expected. There is a period in cosmic history that astronomers call cosmic noon. It sounds almost peaceful. It is the opposite. Cosmic noon refers to a window of time roughly 2 to 4 billion years after the Big Bang, when the universe was producing stars at a rate that dwarfs anything happening today. Galaxies across the cosmos were lit up like furnaces, converting gas into stars with an intensity that the modern universe simply does not replicate. The universe today is comparatively quiet, old, slow, running down. But cosmic noon was the peak, the era when most of the stars that populate the universe today were forged in vast, turbulent clouds of gas and dust, in galaxies churning through their raw material at extraordinary speed. A single major galaxy during cosmic noon might have been forming stars at a rate 100 times higher than what our own galaxy produces today. Astronomers knew cosmic noon existed before Webb. Hubble and ground-based telescopes had identified it through surveys of galaxy populations at different distances, effectively different time periods. But those observations had limited resolution and limited infrared access, meaning the picture of what galaxies actually looked like during that era was blurry and incomplete. Webb changed that. When Webb aimed at galaxies from the cosmic noon period, it resolved their internal structure in unprecedented detail. Scientists could see individual star-forming regions within galaxies that, from Earth's perspective, span less than a fraction of an arcsecond in the sky. They could map where the star formation was happening, how the gas was moving, how dust was distributed, and how different regions of the same galaxy were evolving at different rates. What they found was not a smooth, uniform burst of star formation. It was chaotic, clumpy, violent. Galaxies during cosmic noon looked nothing like the smooth, spiral-armed structures we associate with mature galaxies today. They were irregular, colliding, feeding on streams of cold gas falling in from the surrounding cosmic web. Some were in the process of merging with other galaxies, triggering enormous bursts of star formation in the collision zones. One Webb observation revealed a galaxy during cosmic noon that had already formed a compact, dense core of old stars, while its outer regions were still furiously building new ones. That combination suggested the galaxy's center had finished its main growth phase and gone quiet while the outskirts were still active, which challenged the expectation that galaxies build from the inside out, uniformly. That single observation implied the process of galaxy growth was more fragmented, more spatially complex than the models assumed. Different parts of the same galaxy could be at different stages simultaneously, not because of some exotic process, but simply because gravity, gas supply, and feedback from young stars do not act uniformly across a whole galaxy at once. Here is what that means for the star maps. If galaxy formation during cosmic noon was more complex and more rapid than models assumed, then the stellar populations those galaxies produced were also different from what the models predict. Different stellar populations age differently. They change color at different rates. When astronomers use galaxy colors to estimate ages and distances, they rely on models of how stars evolve. If those models are calibrated on the wrong assumptions about early star formation, the distance estimates carry another layer of error. Every distance measurement to every galaxy at that epoch passed through assumptions about stellar evolution that Webb is now stress testing. And earlier than cosmic noon, in the universe's true infancy, Webb found something that pushed the problem to a completely different scale. Gravity is patient. That is the key assumption underlying every model of galaxy formation ever built. After the Big Bang, matter was spread almost uniformly across space. Almost. There were tiny differences in density, regions where matter was fractionally more concentrated than neighboring regions. Gravity began pulling on those differences immediately, drawing matter toward the denser spots and away from the emptier ones. Over hundreds of millions of years, the dense regions grew denser, eventually collapsing into the first stars and galaxies. This process has a speed limit. Gravity works steadily, but it cannot assemble enormous structures instantly. Matter has to fall inward, collide, heat up, radiate energy, cool down, and collapse further. Stars have to ignite, burn, explode, and enrich the surrounding gas with heavier elements before the next generation forms more efficiently. Building a massive galaxy, one containing hundreds of billions of stars, takes time measured in billions of years, layered through multiple cycles of this process. The most precise computer simulations of galaxy formation, run on the largest supercomputers available, encode all of this physics and produce a universe that looks broadly like the one we observe today. Those simulations produce galaxies at the right sizes, in roughly the right numbers, at roughly the right times, except at the very early end of the timeline. And that exception is growing sharper as Webb sends back more data. Webb has now identified multiple galaxies from a period when the universe was only 400 to 600 million years old that contain stellar masses comparable to the Milky Way or larger. These are confirmed findings, published in peer-reviewed research, not preliminary speculation. Some of these objects contain a mass equivalent to tens of billions of times the mass of our own star, assembled in a fraction of the time the standard models say is physically possible. To understand why this is so disruptive, consider what the simulations require. To build a galaxy that massive that early, you need dense enough patches of matter in the early universe to collapse rapidly, efficient enough star formation that the collected gas converts quickly into stars, and a suppression of the feedback effects that normally slow star formation down. Feedback is the process by which young, massive stars blast radiation and stellar winds into the surrounding gas, heating it, pushing it outward, and throttling the rate of further star formation. It is the galaxy's own built-in brake system. If early galaxies were forming stars fast enough to build the masses Webb observes, either the feedback brake was far weaker than assumed, or the initial density fluctuations in the early universe were far stronger than our measurements of the ancient radiation field suggest, or both. All three possibilities require changing something in the standard model. A team of researchers, after analyzing a collection of these unexpectedly massive early galaxies, described the situation as a tension between the data and the simulations that they could not resolve through parameter adjustment alone. In other words, they could not simply tune the existing models to fit what Webb was showing them. The gap was too large. The honest scientific position, and the position most researchers in this field hold right now, is that we do not fully understand how the universe built its first large structures. Webb has confirmed that those structures existed. The mechanism that produced them remains an open question. But Webb did not stop at finding massive galaxies in the early universe. It found something about their shapes that made the problem dramatically stranger. Shape matters more than you might expect. A galaxy's structure is the record of its history. Irregular, chaotic galaxies are young, still assembling, still experiencing the violent collisions and accretion events that drive early growth. Smooth elliptical galaxies are typically old, having burned through their gas and settled into a stable shape over billions of years. And spiral galaxies with their organized rotating disks and sweeping arms represent a specific stage of evolution that requires a long, relatively calm period of ordered rotation to develop and maintain. Spiral structure is delicate. Mergers destroy it. Interactions with neighboring galaxies distort it. The organized arms only persist when a galaxy rotates smoothly for long enough that density waves can propagate through the disk and reinforce the pattern. Building a clean spiral takes time, and more importantly, it requires the absence of the kind of violent events that dominate the early universe. The early universe was expected to be a place of constant collision, constant disruption, constant chaos. Everything was closer together, moving faster relative to neighbors, undergoing mergers far more frequently than galaxies do today. A pristine spiral galaxy surviving in that environment was not something the models predicted for the universe's first few 100 million years. Webb found one anyway. A galaxy now referred to as the Firefly Sparkle sits at a distance corresponding to a time when the universe was roughly 800 million years old. Webb resolved it into a structured system of star clusters, arranged with unexpected regularity, showing early organization far more advanced than models predicted at that age. Other observations pushed further. A separate analysis of Webb data identified multiple candidates for disk galaxies, the category that includes spirals, at redshifts corresponding to the universe's first few 100 million years. Some of these candidates require follow-up confirmation, and researchers are appropriately cautious about claiming certainty for objects at the edge of Webb's detection capability. But the pattern is accumulating across multiple independent teams. The finding that hit hardest came from a survey that systematically searched Webb's early universe images for disk-shaped galaxies. The survey found them at a rate approximately 10 times higher than state-of-the-art simulations predicted for that epoch. 10 times. A simulation off by 10% is a calibration issue. Off by 10 times is a different category of problem. One proposed explanation is that the early universe had a smoother, calmer, dynamical environment in certain regions, than the global average suggests, allowing some galaxies to avoid the disruptive mergers that should have been constant. Another proposal involves the role of dark matter halos, suggesting that certain configurations of dark matter provided a more stable scaffolding for disk formation than models assume. A third possibility, which researchers mention carefully because it has large implications, is that the early universe's expansion history was different enough from what the standard model predicts that the rate of galaxy-disrupting interactions was lower than calculated. If the universe expanded slightly differently in its first billion years, the spacing between galaxies and the frequency of collisions would both shift. That possibility connects back to the Hubble tension in an unexpected way. A different expansion history in the early universe would shift the cosmic background radiation measurement. It might explain why the early universe's measurement and the late universe's measurement produce different expansion rates. And that explanation, if it holds, would require rewriting not just our models of galaxy formation, but the physics of what was driving the universe's expansion in its earliest moments. Whatever was driving it, Webb is now pointing directly at the evidence. And what it found about dark matter's role in all of this is where things get genuinely strange. Dark matter holds the universe together. That sentence is not poetic. It is the working conclusion of decades of observation across every scale of cosmic structure. Galaxies spin too fast. If you calculate how much gravity the visible matter in a galaxy can produce, and then measure how fast the outer edges of that galaxy are rotating, the math does not work. The outer stars rotate at speeds that should fling them off into intergalactic space. If visible matter were the only gravitational source, something else must be holding them in. That something is dark matter, a substance that interacts through gravity, but produces no light and leaves no electromagnetic trace. The standard model of cosmology treats dark matter as cold. Cold, in this context, means the dark matter particles were moving slowly in the early universe, allowing gravity to pull them into dense clumps efficiently. Cold dark matter clumps on small scales first, building small structures that then merge into larger ones. This hierarchical process, small to large, is a core prediction of the standard model. It works beautifully on large scales. The distribution of galaxy clusters, the vast cosmic web of filaments, and the overall pattern of structure in the universe all match cold dark matter predictions with impressive precision. It struggles on small scales. The number of small satellite galaxies around large galaxies, the density of dark matter at galaxy centers, and the internal structure of dwarf galaxies all show discrepancies with the cold dark matter predictions that have nagged at cosmologists for years. Researchers have proposed solutions, mostly involving how ordinary matter interacts with and reorganizes dark matter through feedback processes. Those solutions work partially. Webb is now piling on new constraints from the early universe direction. If dark matter is truly cold and hierarchical, then the first structures in the universe should be small, and large structures should take time to assemble. Webb's massive early galaxies challenge that expectation directly. For those galaxies to exist at the masses and epochs Webb observes, dark matter halos of sufficient size had to exist before them, providing the gravitational wells into which gas could fall and form stars. Building those halos quickly enough, under cold dark matter physics, strains the models. Some researchers have begun revisiting a class of dark matter models called warm dark matter, where the particles move faster and smooth out small-scale fluctuations while still allowing large-scale structure to form. Warm dark matter makes different predictions about the number of small galaxies and the internal density profiles of galactic cores, and some of those predictions fit certain observations better than cold dark matter does. Others are exploring ultralight dark matter, sometimes called fuzzy dark matter, in which the particles have wave-like quantum properties that suppress clumping below a certain scale. This model produces a specific kind of large-scale structure while suppressing the formation of the smallest galaxies, potentially solving the small-scale problems simultaneously. Neither model is confirmed. Both remain theoretical frameworks being tested against observations. Webb is generating the observations that will constrain which, if any, of these alternatives can replace cold dark matter as the standard. Every massive early galaxy Webb confirms is a data point that warm and cold dark matter models must explain. Every well-resolved dwarf galaxy in the nearby universe is another constraint. The dark matter question is not yet broken open. It is under active pressure from Webb data, and the pressure is building through a specific physical mechanism, one involving early star formation, that takes the impossibility of those early massive galaxies and adds an even stranger layer. Stars do not form easily. That sounds counterintuitive, but the universe makes star birth genuinely difficult. A cloud of gas collapsing under its own gravity heats up as it compresses. Heat generates pressure. Pressure pushes outward and resists further collapse. If the gas cannot radiate away that heat fast enough, the collapse stalls, the cloud bounces back, and star formation stops before it begins. This is why most gas in galaxies today never becomes stars. Most of it just sits there, slowly cycling through clouds that collapse partially, heat up, and disperse again. The fraction of available gas that actually converts into stars over a given time period is called the star formation efficiency. In the modern universe, across most galaxies, that number is quite low. For a typical star-forming region, only a small fraction of the gas in a molecular cloud ends up locked into stars before feedback from the new stars themselves, the radiation, winds, and eventual supernovae heats and disperses the remaining material. The standard models of galaxy formation are built around these observed efficiency rates. They assume efficiency in the early universe was broadly similar, perhaps somewhat higher due to different gas compositions and temperatures, but within the same order of magnitude. Webb's observations of massive early galaxies require a different answer. Back calculating from the stellar masses Webb observes in those early galaxies, and knowing how much gas was realistically available in the early universe for those galaxies to draw from, researchers derived the star formation efficiency required to produce those masses in the available time. The answer in several cases was not modestly higher than modern rates. It was dramatically, uncomfortably higher. Some analyses point toward efficiencies approaching or exceeding 50% of available gas converted into stars, far above the few percent that normal physics and feedback processes would allow. A team publishing in a leading astrophysics journal described these objects as potentially requiring conditions in which feedback was nearly absent or dramatically suppressed during the early growth phase. That is a significant statement. Feedback suppression at that scale has no confirmed physical mechanism in the standard model. One speculative idea being explored is that the initial mass function, the distribution of star masses produced in each burst of star formation, was different in the early universe. If early star formation preferentially produced more massive stars, those stars would burn brighter and die faster, producing more ionizing radiation and more supernovae per unit of time. That sounds like it would make feedback worse, but it also means more chemical enrichment faster, potentially allowing subsequent generations of stars to form more efficiently as the gas became richer in heavier elements. The chemistry of early star formation is one of the most active research areas Webb has opened up. Because Webb can now directly observe the chemical composition of star-forming regions in the early universe through spectroscopy, splitting incoming light into its component wavelengths and reading the absorption lines like a fingerprint. And those chemical fingerprints are showing scientists something about where stars are born that the models did not predict. Something about the raw conditions inside star-forming clouds in the early universe that changes the story of how the first stars ignited. That discovery is coming next, and it is one that touches something as fundamental as the ingredients of stellar birth itself. A nebula is a nursery, a vast cloud of gas and dust, where gravity slowly pulls material together until the pressure and temperature at the core of a collapsing knot become high enough to ignite nuclear fusion. A star is born. That is the clean version of the story, and for decades it was sufficient. Webb is showing the nursery in real time, and what it sees inside contradicts several assumptions about how orderly that process is. Webb's infrared vision pierces dust clouds that block visible light completely. Hubble could photograph the glowing surfaces of nebulae, but the star-forming cores buried inside were hidden behind walls of opaque dust. Webb sees through that dust and into the heart of the collapse itself, watching young protostars flicker to life inside cocoons of gas, and watching the jets of material they eject as they shed angular momentum during formation. The Orion Nebula, one of the most studied star-forming regions in the sky, revealed something immediately unexpected when Webb trained its mirror on it. Astronomers found pairs of objects they initially could not classify, glowing in infrared within the nebula at locations where no known stellar object should be producing that kind of emission. After analysis, many of these objects turned out to be pairs of extremely young, low-mass brown dwarfs, objects too small to sustain full hydrogen fusion, forming in isolation from the main cluster of young stars. The number of these objects was far higher than models had predicted. Standard theories of star formation produce brown dwarfs as occasional byproducts of the normal collapse process. Webb found them in quantities suggesting they form through their own distinct pathway, perhaps through the direct collapse of small, isolated gas fragments rather than as failed fragments of larger stellar collapse events. That distinction matters because the theories of star formation are tied directly to how we model the populations of stars in galaxies. If a significant fraction of star formation events produce brown dwarfs through a separate pathway, then our census of stellar populations, the accounting of how much mass goes into stars of different sizes, needs revision. Revised stellar populations mean revised models of how galaxies produce light. Revised light production models mean revised distance estimates. Webb also found, in the Orion Nebula and in several other nearby star-forming regions, a population of objects it was not looking for at all. These objects, now being called Jupiter mass binary objects, are pairs of objects with masses similar to large planets orbiting each other in open space within the nebula, far from any parent star. They glow in infrared with a warmth that suggests they formed through a gravitational collapse process, similar to star formation, but at a mass scale far too low for hydrogen fusion to ignite. Their existence raises a genuinely open question. How far down in mass does the stellar formation process extend? If gravity can assemble free-floating objects the mass of Jupiter directly from nebular gas, what is the lower limit? And how many of these objects exist in galaxies throughout the universe? Invisible light surveys, undetected until an infrared telescope sharp enough to see them came online. Webb is actively surveying other nebulae to count these objects and map their distribution. Early results suggest the population is large enough to be cosmologically significant. Inside those same nebulae, Webb detected something else entirely. Something about the chemistry of the gas that opened a line of research nobody had expected to pursue this early in the mission. Something involving molecules that should not survive the harsh radiation environment of a star-forming region. The space between stars is one of the harshest environments in the universe. Intense ultraviolet radiation from young massive stars floods through star-forming regions, stripping electrons from atoms and breaking apart molecular bonds. Conventional wisdom said that complex molecules, the kind built from multiple atoms bonded together, would be destroyed faster than they could form in those violently irradiated zones. Webb looked at the inner disk of a young star system, a protoplanetary disk where planets were actively forming around a newly born star, and found water. Abundant water, warm water, sitting in the zone where rocky planets were assembling, less than 3 times the distance that Earth orbits our own star. That finding, published by a team using Webb's mid-infrared instrument, was significant in itself. Water in the planet-forming zone of a young solar system suggests that the building blocks of ocean-bearing worlds like Earth might be a common feature of planetary formation, not a rare accident. But Webb went further. In multiple star-forming regions and protoplanetary disks, Webb detected a range of molecules beyond water: carbon dioxide, methane, benzene, and in at least one disk, a detection of molecules containing carbon-carbon bonds, the backbone structure of organic chemistry, the same molecular framework underlying all known biology. The presence of benzene was particularly striking. Benzene is a ring-shaped organic molecule, 6 carbon atoms bonded in a hexagonal structure. Finding it in a protoplanetary disk means that the chemical reactions that build ring-structured organic compounds, the foundation for amino acids, and eventually proteins in Earth's biology, are already happening in the earliest stages of planetary system formation, before planets have fully assembled. Webb also detected these molecules, not just in protoplanetary disks, but in the diffuse gas of star-forming clouds themselves, at stages before stellar ignition, in material that had not yet collapsed into a disk. This pushes the origin of complex chemistry even earlier in the stellar birth sequence, into the cold, pre-stellar cloud phase. The implication is that planetary systems do not start from scratch in terms of chemistry. They inherit a preloaded stock of organic molecules, directly from the nebula they formed in. Earth's oceans and the organic molecules that preceded life on this planet may have originated, at least in part, in the interstellar chemistry of the cloud that became our solar system, rather than from later delivery by asteroids or comets exclusively. This finding has no direct connection to the Hubble tension or the distance ladder problem, but it reshapes the context in which those problems exist. We are discovering that the universe is more chemically complex, more biologically primed, at its formation stages, than any model had encoded. The universe is not a simple clockwork of gravity and nuclear physics. It is a chemistry laboratory operating at cosmic scales, generating the ingredients of life as a routine product of the stellar birth process. And the very first stars in the universe had none of this chemistry available to them. They were born into a cosmos with no heavy elements, no carbon, no oxygen, no water, because those elements had not yet been forged. The story of how those first stars formed, how they lived and died, and how they seeded the universe with everything that came after, is a story Webb is now reading directly from the most ancient light it can capture. The first stars were monsters. There is no other word that captures the scale accurately. Born into a universe containing nothing but hydrogen and helium, a cosmos with no dust, no carbon, no molecular cooling pathways, of the kind that enable the relatively restrained star formation Webb observes in modern nebulae. Those first stars formed under conditions that pushed them to extremes that have never been replicated since. Modern stars form in cold molecular clouds. The gas cools to temperatures close to absolute zero, slowing the thermal motion of particles and allowing gravity to pull material together into relatively compact, moderate mass objects. Our own star formed this way. Most stars you can see in the night sky form this way. The cooling is efficient because modern interstellar gas is laced with carbon monoxide, water vapor, and other molecules that absorb energy and radiate it away, dropping the temperature of the collapsing cloud. The first stars had none of those molecules. The gas was pure hydrogen and helium, and it could only cool through much less efficient atomic processes. That inefficient cooling meant the gas stayed hotter during collapse, building up higher pressure that could only be overcome by accumulating more mass. The collapsing fragments grew larger and larger before the conditions for nuclear ignition were met. Scientists calculate, through theoretical modeling that is confirmed by what Webb observes of the chemical aftermath of those stars, that the first generation of stars likely ranged from several tens to potentially several hundreds of times the mass of our own star. Some theoretical models allow for even more extreme cases. These objects were so massive that their cores burned at temperatures far exceeding those of modern stars, racing through their nuclear fuel at a ferocious pace. A star with 100 times the mass of our own star does not live 100 times as long. It lives a tiny fraction as long. The lifetime of a star decreases sharply with mass. A star like our own persists for roughly 10 billion years. A star 100 times more massive may survive only a few million years, barely a cosmic eye blink. Some of the most massive first-generation stars may have lived for only 1 or 2 million years before their cores could no longer sustain fusion and collapsed catastrophically. The way they died was different too. Modern stars below a certain mass threshold explode as supernovae and leave behind a neutron star or black hole. The most massive first-generation stars, above a critical mass threshold, may have undergone something more extreme, a pair instability supernova, in which the core becomes so energetic that it begins spontaneously converting energy into matter-antimatter pairs, draining the pressure that holds the star up and triggering a collapse followed by a total annihilation explosion that leaves no remnant at all. The entire star, every atom of it, becomes radiation and shrapnel blasted into the surrounding gas. Webb cannot directly observe those first-generation stars. They are too ancient, too brief, and their light has been redshifted beyond even Webb's infrared range by the expansion of the universe over 13 billion years. But Webb can read what they left behind, the chemical composition of the second-generation stars that formed from their remnants, detectable in the spectra of ancient stars in nearby dwarf galaxies, and in the diffuse gas of the early universe. Carries the signature of what those first giants produced, And what those signatures are beginning to reveal about the elements forged in the first stellar deaths is something that touches not just the history of stars, but the origin of every atom inside your body. That is where we go next. When the first stars died, the universe changed forever. Before those deaths, the cosmos contained two elements in meaningful quantities: hydrogen and helium. Everything else, every atom on the periodic table beyond those two, was absent. Carbon, oxygen, nitrogen, iron, calcium, the elements that build planets, oceans, atmospheres, and living things, did not exist anywhere in the observable universe. The cosmos was chemically barren. Then, the first massive stars collapsed and exploded. Nuclear fusion inside a massive star is a layered process. In the core, hydrogen fuses into helium. As the helium builds up, gravity compresses it until helium fuses into carbon and oxygen. Carbon and oxygen fuse into heavier elements still. The process continues, each stage requiring higher temperatures and pressures, producing a star with a structure like an onion, layers of progressively heavier elements surrounding a core that is burning through its final nuclear fuel. Silicon fusion eventually produces iron, and iron is where fusion stops. Iron absorbs energy rather than releasing it. When an iron core builds up to a critical mass, the star's internal support collapses in less than a second, and the outer layers fall inward, then rebound in a catastrophic explosion. That explosion, a core collapse supernova, does two things of enormous consequence for everything that came after. First, it synthesizes additional heavy elements in the extreme conditions of the explosion itself, including many elements heavier than iron that cannot be produced in stellar cores during normal burning. Second, it ejects all of those elements, all the layers of carbon, oxygen, silicon, sulfur, and heavier elements the star spent millions of years building, into the surrounding gas at a fraction of the speed of light. The ejected material mixes with the surrounding hydrogen and helium, enriching it chemically. When that enriched gas later collapses into new stars, those stars form with a small but critical fraction of heavy elements already present. Those heavy elements change everything about how the next generation of stars behaves, how they cool during collapse, what kinds of planets form around them, and what chemistry becomes possible in the disk of gas and dust surrounding each new star. The pair instability supernovae of the most massive first-generation stars were even more chemically productive, because the entire star was disrupted. Rather than just its outer layers, the explosion released the full inventory of every element that star had synthesized across its entire interior. A single pair instability supernova from a star several hundred times the mass of our own star could enrich an entire giant cloud of gas with enough carbon, oxygen, and silicon to measurably shift its chemistry away from pure hydrogen and helium. Webb is reading those chemical signatures today by observing the spectra of extremely old, chemically primitive stars in the halo of our galaxy and in nearby dwarf galaxies, and by detecting the chemical composition of ancient gas clouds in the early universe through absorption features in the light of distant quasars. Webb is building a direct observational record of what those first stellar explosions produced. Some of those ancient stars carry chemical abundance patterns that match the predicted yields of pair instability supernovae strikingly well. The ratios of calcium to iron, of carbon to magnesium, of certain trace elements that serve as fingerprints of specific nucleosynthesis processes, line up in ways that point specifically to the death of extremely massive first-generation stars as their origin. The calcium in your bones traces back to an explosion that happened more than 13 billion years ago. The oxygen in every breath you take was forged in the core of a star that lived for less than 2 million years and died before Earth existed. The iron carrying oxygen through your blood right now was synthesized in stellar collapse and scattered across space by a shockwave traveling at tens of thousands of miles per second. You are, in the most literal physical sense, the ash of dead stars. Webb is finding those original stars' fingerprints, and what it is detecting in the chemistry of the earliest gas in the universe appeared far sooner than anyone expected. The timeline of chemical enrichment was supposed to follow a simple logic. First-generation stars form, live, and die. Their deaths scatter heavy elements into the surrounding gas. That gas mixes slowly. Eventually enough mixing occurs that the next generation of stars forms with measurable heavy element content. The process takes time, hundreds of millions of years at minimum, before the universe's gas becomes meaningfully enriched beyond hydrogen and helium. Webb looked at the chemistry of the universe during its first billion years and found carbon and oxygen already present in quantities that should not be there yet. Spectroscopy is the tool Webb uses to read chemical composition at cosmic distances. When light from a distant source passes through gas, the gas absorbs specific wavelengths corresponding to specific atomic transitions, each element leaving its own unique barcode of missing colors in the spectrum. Webb's instrument split incoming light into its component wavelengths with extraordinary precision, reading those barcodes and identifying which elements are present in gas clouds billions of years in the past. A team analyzing Webb spectra of gas surrounding some of the earliest known quasars, brilliant cores of active galaxies powered by growing black holes, found carbon and oxygen absorption signatures at redshifts corresponding to a time when the universe was only 400 to 500 million years old. The abundances were modest compared to modern interstellar gas, but measurably above the background level of pure primordial hydrogen and helium. For carbon and oxygen to be present in that quantity at that epoch, a substantial population of massive stars had to have already formed, lived their brief lives, and exploded, scattering their synthesized elements into the surrounding gas. And that gas had to have mixed enough for the signatures to be detectable. All of that stellar evolution had to occur within the first 400 to 500 million years of cosmic history. The models said that timeline was tight. Some said it was too tight, generating enough massive stars, running them through their full life cycle, exploding them, and mixing the products into the surrounding medium, all within that window required assumptions about early star formation efficiency and clustering that pushed against the constraints of the standard model. Webb's detections did not immediately falsify those models. Scientists are careful about that distinction, but the detections placed the early enrichment timeline at the most compressed end of what the models could accommodate, and in some cases slightly beyond it, suggesting that either early stars were forming and dying faster than assumed, or in greater numbers per unit volume of gas, or both. A separate Webb observation added a specific and striking data point. Spectroscopic analysis of a galaxy existing when the universe was only about 400 million years old showed the presence of doubly ionized oxygen, a chemical state that requires extremely energetic ultraviolet radiation to produce. The presence of that ionization state meant the galaxy contained very massive, very hot young stars generating intense radiation fields. Those stars existed in a galaxy that had already undergone significant chemical enrichment. In other words, the galaxy was already on its second or third generation of stars by 400 million years after the Big Bang. It had formed stars, those stars had lived and died and enriched the gas, and a new generation of even more efficiently forming stars had ignited in the enriched medium, all within the universe's first 400 million years. That compressed, multi-generational stellar history inside a single young galaxy is exactly the kind of finding that strains the standard model's timeline. And it connects directly to another mystery Webb has been probing in those same early galaxies: why some of them stopped forming stars abruptly, completely and far earlier than any mechanism in the model can account for. Some galaxies go quiet. They stop forming stars entirely, their gas supply cut off or depleted, their stellar populations aging slowly toward red and dim. In the modern universe, these dead galaxies are common, mostly massive ellipticals sitting at the centers of galaxy clusters, their star formation quenched long ago by processes that are reasonably well understood. Webb found dead galaxies in the early universe, galaxies that had already stopped forming stars when the universe was less than 1 billion years old. That should not be possible at the scale Webb is observing. Quenching, the technical term for shutting down star formation, requires a mechanism. Something must heat or remove the gas that would otherwise collapse into stars. In the modern universe, the leading mechanisms are well studied. Active galactic nuclei, the energetic jets and radiation produced by supermassive black holes at galaxy centers, can heat the surrounding gas and prevent it from cooling enough to collapse. Supernova-driven winds from intense bursts of star formation can push gas out of smaller galaxies entirely. Hot gas in galaxy clusters can strip cold gas from infalling galaxies through ram pressure. All of these mechanisms take time to operate effectively. They require a galaxy to first build up a substantial stellar population, produce enough supernovae to drive significant winds, or grow a black hole massive enough to influence the surrounding gas on galactic scales. Doing all of that, and then quenching star formation completely, within the universe's first 800 million years, was not something the models predicted for galaxies of the masses Webb is finding quenched at that epoch. A team confirmed the quenched status of several early massive galaxies through Webb spectroscopy. Their spectra showed the characteristic signature of old stellar populations, the dominance of red. Cool stars with no emission lines indicating active star formation, at redshifts corresponding to a time when the universe was less than 1 billion years old. The galaxies were massive. Their star formation was definitively over, and nothing in the standard model's toolkit of quenching mechanisms operated fast enough to explain the shutdown. One proposal that has gained traction involves the role of supermassive black holes growing faster than models allow in the early universe. A sufficiently massive and active black hole at a galaxy's center, accreting material and driving powerful jets of radiation and particle outflows, could in principle heat and expel the galaxy's gas supply rapidly enough to match what Webb observes. The problem is that this solution requires those black holes to have grown to enormous masses extraordinarily quickly, which raises its own set of questions about how black hole growth works in the early universe. Those questions connect to a Webb discovery that stands as one of the most dramatic findings of its early mission. A finding about a black hole that was already impossibly large by the time the universe was barely a few 100 million years old, one that challenges the known physics of how these objects are born and grow. That finding is where we go next, and it pulls everything in this story into a sharper focus. The relationship between a galaxy and the supermassive black hole at its center is one of the most studied puzzles in astrophysics. In the modern universe, that relationship looks like a tight partnership. The mass of a galaxy's central black hole tracks closely with the mass of the galaxy's central bulge of stars. Regardless of the galaxy's size, location, or age, small galaxies have smaller black holes. Massive galaxies have more massive ones. The ratio holds across an enormous range of galaxy types. That correlation implies a shared history. The galaxy and its black hole grew together, each influencing the other's development through a feedback loop spanning billions of years. When the black hole grows rapidly, it floods the galaxy with energy that slows star formation. When star formation slows, less gas falls toward the center, and black hole growth slows too. The two components regulate each other, arriving eventually at the observed proportional relationship. That coevolution story is built on observations of the modern universe and on simulations calibrated to match those observations. It makes a specific prediction. In the early universe, when galaxies were young and still assembling their stellar mass, black holes should be comparably young and comparably small. The partnership was supposed to begin together and grow together. Webb found black holes in the early universe that are too massive relative to their host galaxies by factors that the coevolution model cannot accommodate. Multiple Webb observations have now identified quasars and active galactic nuclei in the early universe, meaning objects where the central black hole is actively accreting material and producing enormous luminosity that are far more massive than their host galaxies should be able to support under the standard coevolution framework. In some cases, the black hole appears to contain a significant fraction of the total stellar mass of the entire host galaxy, a ratio that in the modern universe would be extraordinary and is essentially absent from the observed population. One interpretation is that in the early universe, black holes got a head start. They grew faster than their host galaxies in the earliest epochs, perhaps seeded by different mechanisms than assumed, or fed by gas flows that operated independently of the star formation processes building the galaxy around them. The galaxy then grew to match the black hole over subsequent billions of years, arriving at the tight relationship we observe today, only after a period of imbalance in the early universe. That interpretation is reasonable and scientifically coherent, but it requires explaining how those black holes grew so large, so quickly, and that explanation, when followed to its logical conclusion, leads to a place where standard physics of black hole growth runs directly into an observational wall. Because the most extreme cases Webb has found involve black holes that are not just somewhat oversized for their host galaxies. They are billions of times the mass of our own star, present when the universe was only a fraction of its current age, growing at rates that push against or exceed the theoretical maximum rate at which any black hole can accrete material. That theoretical maximum is not an estimate. It is derived from fundamental physics, and it gives the universe less time than it has apparently spent to build what Webb is finding inside it. Webb found a black hole weighing close to 1 billion times the mass of our own star in a galaxy that existed when the universe was only 600 million years old. Sit with that number for a moment. 600 million years sounds like a long time. On the cosmic timeline, it is barely a breath. The universe had barely finished its initial formation of the first stars and galaxies. The earliest supernovae were still seeding the first heavy elements into the primordial gas. And somewhere in that infant cosmos, a black hole was already fully mature, monstrous, and actively consuming material at a rate that made it shine brighter than entire galaxies surrounding it. The object, identified through Webb spectroscopy and confirmed across multiple independent analyses, is classified as a quasar. Its black hole's mass was derived from the motion of gas swirling around it, a reliable technique calibrated across thousands of black hole mass measurements in the nearby universe. The measurement's uncertainty range is real and acknowledged by the researchers, but even the lower bound of that uncertainty places the object in a category that standard models struggle to populate. Here is the specific problem. Black holes grow by accreting material, pulling in gas and dust from their surroundings, adding mass over time. The rate at which a black hole can accrete is limited by radiation pressure. As the black hole consumes material, the infalling gas heats up and produces intense radiation that pushes back against further infall. At a certain accretion rate, called the Eddington limit, the outward radiation pressure exactly balances the inward pull of gravity, and accretion stalls. Sustained accretion at the Eddington limit represents the theoretical maximum growth rate for a standard black hole. Starting from a stellar remnant black hole of a few tens of times the mass of our own star, growing continuously at the maximum Eddington rate without interruption, a black hole would need roughly 800 million years to reach 1 billion solar masses. The universe was 600 million years old when the object Webb found already existed at that mass. The math does not close. Even under the most optimistic assumptions about early seed black holes and sustained Eddington limited accretion, the timeline is too compressed. Something either grew faster than the Eddington limit allows, started from a much larger seed than a stellar remnant, or the standard understanding of early black hole physics is missing a mechanism. Each of those possibilities has different implications for physics. Growing faster than the Eddington limit, called super Eddington accretion, is theoretically possible in exotic conditions and has some observational support in nearby systems. But sustaining it long enough and at large enough scales to build 1 billion solar mass black hole in 600 million years requires conditions that remain unconfirmed. Starting from a larger seed black hole is the solution that has attracted the most theoretical attention. If the first black holes in the universe formed not from stellar collapse, but from the direct collapse of entire massive gas clouds, without any intermediate stellar phase, they could begin at masses millions of times larger than stellar remnants, giving them a massive head start on the growth timeline. That idea had been purely theoretical for years. Webb is now finding the observational candidates that could test it. And the theory itself, when examined closely, implies a process in the early universe so extreme and so unlike anything operating today, that confirming it would force a substantial revision of how we understand the first billion years of cosmic history. The Eddington limit is not a suggestion, it is a consequence of fundamental physics, and it sets a hard ceiling on how fast a standard black hole can grow. When gas falls toward a black hole, it does not fall straight in. It forms a swirling disk heated by friction and compression to millions of degrees, radiating enormous amounts of energy. That energy, in the form of photons carrying momentum, pushes outward on the infalling material. At the Eddington limit, the radiation pressure from the accreting material exactly cancels the gravitational pull, drawing new material in. Push a black hole past that limit, add too much material too fast, and the radiation it produces blows the excess away, throttling its own growth rate. This self-regulation is why black holes cannot simply grow at any arbitrary rate. The physics is self-limiting. The universe does not allow black holes to eat without limit. They radiate away the energy of their meals, and that radiation enforces the speed constraint. Now consider the consequences for the timeline. The first stars that died and left stellar remnant black holes produced seeds of perhaps tens to a few hundreds of solar masses. Those seeds began accreting in the dense gas-rich environment of early galaxies. Even accreting at the maximum Eddington rate, continuously doubling in mass approximately every 50 million years. Those seeds need close to 1 billion years to reach the billion solar mass range. The universe, at 600 million years, gave those seeds 300 million years less than the minimum required time. Super Eddington accretion, where a black hole consumes material faster than the radiation pressure limit would normally allow, is the first proposed escape from this contradiction. It is physically possible under specific conditions where the accreting material is funneled in so rapidly that the radiation cannot escape efficiently, reducing its braking effect. Some observations of nearby ultraluminous X-ray sources suggest this process operates in certain environments. But whether super Eddington accretion can operate continuously at the scale and duration needed to grow the black holes, Webb is finding remains undemonstrated. The process is unstable in theoretical models. Maintaining it for hundreds of millions of years without interruption would require very specific conditions that are difficult to sustain in the chaotic environment of an early galaxy. The second escape route involves the seed mass. If the first black hole started enormously massive, the math changes. A seed of 10 million solar masses, for example, needs far fewer doubling times to reach 1 billion solar masses. The question then becomes where that seed came from. Stellar collapse cannot produce it. Something different had to occur. This is where the direct collapse scenario enters the picture, and it is where Webb's observations are most actively shaping the theoretical debate, because Webb can now observe the conditions in early galaxies with enough detail to test whether those conditions could plausibly support a process that, until recently, existed only in theorists' equations. The specific mechanism, the way a massive gas cloud could bypass the stellar phase entirely and collapse directly into a black hole of millions of solar masses, involves a set of conditions that were thought to be extraordinarily rare, perhaps impossibly rare in the real universe. Webb is making those conditions look less rare than assumed, and what it is finding about those direct collapse candidates is where the story becomes genuinely strange, because it involves a process that the universe only had a narrow window in its earliest history to execute, and that window is now closing as Webb watches in real time. For a stellar remnant black hole to grow into a supermassive one, it needs time. Too much time, as Webb's observations are confirming. So theorists proposed a different starting point, a shortcut. The idea is called direct collapse, and it goes like this. In the very early universe, before most of the first stars had formed and died, there existed regions of extremely dense, extremely massive gas clouds, primarily hydrogen and helium, in the initial proportions the Big Bang produced. If one of those clouds could be prevented from fragmenting into individual stars, prevented from cooling efficiently enough to break into smaller clumps, the entire cloud might collapse as a single object directly into a black hole of enormous mass. The obstacle is cooling. Under normal circumstances, a large gas cloud will begin cooling as it collapses, dropping in temperature until molecular hydrogen forms, and molecular hydrogen cools gas very efficiently, allowing it to fragment into smaller and smaller pieces, each of which becomes a star. To prevent fragmentation and allow direct collapse, the molecular hydrogen must be destroyed before it can cool the cloud. The mechanism proposed to accomplish this is intense ultraviolet radiation from a nearby star-forming region. If a galaxy rich with young, massive stars sits close enough to the collapsing cloud, the ultraviolet radiation it produces can dissociate molecular hydrogen, stripping apart the molecules faster than they reform. The cloud then cannot cool efficiently, cannot fragment, and can collapse as a unit into what theorists call a direct collapse black hole, with a starting mass potentially in the range of tens of thousands to hundreds of millions of solar masses. The conditions required are specific. The ultraviolet source must be close enough to be effective, but not so close that its radiation heats the cloud and prevents collapse entirely. The gas cloud must have the right mass and density. The surrounding environment must not be too metal-enriched, because heavy elements provide additional cooling channels that would enable fragmentation even without molecular hydrogen. These requirements seemed, to many astrophysicists, like too narrow a coincidence for direct collapse to be a common occurrence. The theoretical mechanism was sound, but the observational candidates were absent. No confirmed direct collapse black hole had ever been identified. Webb changed the conditions of that search. A team analyzed Webb observations of two compact, intensely luminous objects in the early universe, existing when the universe was less than 1 billion years old, that showed properties inconsistent with ordinary stellar black hole seeds grown through standard accretion. Their masses, estimated from their luminosity and the dynamics of surrounding gas, pointed towards seeds of at least 1 million solar masses. Their host galaxies showed evidence of proximity to intense star-forming regions, exactly the configuration the direct collapse scenario requires. The team published these as candidate direct collapse black holes, the most credible observational candidates for that class of object ever identified. The caveat was clear: these are candidates, not confirmed detections. Alternative explanations remain possible and require further observation to rule out. But the existence of credible candidates, where previously there were none, means the hypothesis moved from theoretical curiosity to active observational target. Webb is now deliberately searching for more of these objects, and the early results of that search suggest they may be more common than the narrow formation conditions imply. If direct collapse black holes are confirmed as a real and significant channel of early black hole formation, it rewrites not just the story of how supermassive black holes grow, but the story of how the first galaxies organized themselves around those black holes in the universe's earliest epoch. And it connects directly to another process Webb is now observing in real time, one that shaped the entire structure of the observable universe, and that was still actively unfolding during the era Webb can now image directly. There was a time when you could not see across the universe, a time when light could not travel freely because the space between galaxies was filled with a fog of neutral hydrogen, so dense that photons were absorbed almost immediately after being emitted. The universe was dark, opaque, closed. Then, the first stars and galaxies turned on, flooding the cosmos with ultraviolet radiation. That radiation stripped electrons from the neutral hydrogen fog, ionizing it, making it transparent. Over hundreds of millions of years, the fog cleared. The universe opened up. Light could travel freely across billions of light years for the first time. This process is called reionization, and it is one of the most important phase transitions in cosmic history. Understanding exactly when it happened, how quickly it progressed, and what drove it reveals the nature of the first luminous objects in the universe and sets the stage for everything that came after. Before Webb, the timeline of reionization was established through observations of quasars at the edge of the observable universe. Light from those distant quasars passed through the intervening gas of the early universe, and astronomers could read the opacity of that gas from the patterns of absorption in the quasar spectra. The data suggested reionization was mostly complete by the time the universe was about 1 billion years old, but the detailed progression, how it started, how it spread, and what contributed most to driving it, remained poorly constrained. Webb's ability to observe individual galaxies deep in the reionization era has changed this completely. Webb can now directly image galaxies from the period when reionization was actively underway, and through spectroscopy, it can measure those galaxies' ultraviolet output, how much ionizing radiation they were producing and injecting into the surrounding gas. By mapping which regions of the early universe had already been cleared of neutral hydrogen and which were still opaque, Webb is building a spatial picture of how reionization progressed patch by patch, rather than uniformly across the cosmos. The early results suggest reionization was driven primarily by large numbers of small, faint galaxies, rather than by the rare, extremely luminous quasars that were previously assumed to be the dominant ionizing sources. Webb keeps finding these small galaxies in the reionization era in much higher numbers than predicted, and their collective ultraviolet output appears sufficient to account for the clearing of the cosmic fog without requiring the quasars to do the heavy lifting. That finding has a significant implication. The standard model weighted quasars heavily in reionization calculations, because they were the most easily observed objects at those distances. If small galaxies dominate, then the reionization timeline itself needs recalibration, because the galaxy population's buildup and its photon output follow a different time profile than the quasar population's evolution. A refined reionization timeline also affects how we interpret the structure of the early universe. The distribution of ionized and neutral regions during the reionization process leaves an imprint on the cosmic background radiation and on the large-scale structure of the galaxy distribution. If reionization proceeded differently than assumed, the imprint left in the data we use to measure the early universe's density and expansion changes, feeding back into the cosmological model and potentially shifting the early universe's measurement of the expansion rate. The thread connecting reionization, the cosmic background radiation, and the Hubble tension is subtle but real. And Webb is pulling on that thread through one more set of observations, aimed at the most invisible structure in the universe, the dark scaffolding that holds everything together. The light from a distant quasar carries a secret, not the quasar's light itself, but the marks left on it by everything that light passed through on its journey across billions of light years of space. As quasar light travels, it encounters clouds of hydrogen gas distributed through the intergalactic medium. Each cloud absorbs a specific wavelength of light, leaving a narrow dark line in the quasar's spectrum. A single cloud produces a single line. Many clouds at many different distances produce many lines at many different wavelengths, because the expansion of the universe stretches each absorption line by an amount proportional to the cloud's distance. The result is a spectrum crossed by dozens or hundreds of narrow dark lines, each one marking the location of a hydrogen gas cloud somewhere along the line of sight. Astronomers call this pattern the Lyman alpha forest. It looks like a barcode, and like a barcode, it encodes information. The density of lines in the Lyman alpha forest tells you how much gas exists at different distances along the line of sight. The clustering of those lines, which positions have many clouds and which have few, maps out the large-scale structure of the intergalactic medium. And because gas in the universe is not randomly distributed, but is organized by the gravity of dark matter into a specific pattern of filaments, walls, and voids, the Lyman alpha forest is effectively a three-dimensional map of dark matter's invisible skeleton. Webb can observe quasar spectra at distances, and therefore at epochs, that were previously inaccessible. The earliest quasars visible in Webb data sit at redshifts corresponding to the reionization era, when the universe was still partially opaque. The Lyman alpha forest, in their spectra, is a direct probe of how gas was distributed during that critical period, how dense the neutral hydrogen fog was, and how its clearance progressed. Webb's high-resolution spectroscopy of these early quasars reveals that the neutral hydrogen at the tail end of the reionization era was distributed in a more patchy, inhomogeneous pattern than uniform models assumed. Some sightlines show long stretches of nearly complete opacity, meaning neutral gas extended for enormous distances without being ionized. Other sightlines show transmission, indicating cleared regions. The patchiness maps the progress of reionization as a mosaic rather than a smooth wave. That patchiness has a structural cause. The regions that ionized earliest correspond to areas with the highest density of early galaxies. The regions that stayed opaque longest correspond to underdense voids, where galaxies were sparse, and the ultraviolet radiation needed to clear the hydrogen arrived late. The pattern of clearing traces the underlying pattern of dark matter density. Webb is therefore using early quasar light to indirectly map dark matter in the early universe, reaching back to an epoch where direct galaxy surveys are sparse, and the invisible scaffolding can only be read through its effects on light passing through the gas it organizes. That scaffolding, the cosmic web of dark matter filaments threading through all of space, is one of the most extraordinary structures the universe has ever produced. And Webb is now imaging it at scales and resolutions that are forcing a revision of some of the model's most fundamental predictions about how that web was built and what lies along its strands. The universe has a shape, not the round shape you might imagine from descriptions of an expanding cosmos, but an intricate three-dimensional web of filaments, walls, sheets and voids, spanning hundreds of millions of light years in every direction. Picture a vast three-dimensional spiderweb, except each strand is a filament of dark matter, hundreds of millions of light years long. And along each strand, drawn by that dark matter's gravity, flows ordinary matter. Gas streams down the filaments toward the dense nodes where multiple filaments intersect. Those nodes accumulate matter into galaxy clusters. The galaxies within clusters grew by feeding on that gas, supplied along the filaments like water, flowing through rivers toward a lake. Between the filaments lie enormous voids, nearly empty regions of space where matter is scarce and galaxies almost non-existent. The largest voids in the universe span hundreds of millions of light years, bubbles of near emptiness surrounded by the Webb's luminous filaments and clusters. This structure, called the cosmic web, was predicted by cold dark matter models in the 1980s before computer simulations could reproduce it in detail. The prediction was confirmed observationally through surveys mapping the positions of millions of galaxies in the nearby universe. The agreement between the predicted and observed large-scale structure of the cosmos was one of the great triumphs of the standard cosmological model. Webb is now examining the cosmic web in the early universe, at epochs when the filaments were younger, less developed, and the flow of matter along them was at its most intense. The results are precise enough to trace individual filaments by detecting the faint glow of hydrogen gas streaming along them, illuminated by radiation from nearby galaxies. Several Webb observations have captured filamentary structures in the reionization era, connecting galaxies across distances of tens of millions of light years in the early universe, making them the oldest large-scale structures ever directly imaged. The filaments, Webb observes, are in places consistent with where dark matter models predict them to be, which is a confirmation of the model's large-scale structure predictions at those early epochs. But the galaxies distributed along those filaments, their masses, numbers, and degree of evolution push against the predictions at the smaller scale. Specifically, the most massive and evolved galaxies Webb finds in the early universe tend to cluster preferentially at the nodes of the web, the intersection points of multiple filaments. Exactly as expected, but their masses at those nodes are higher than simulations predict for that epoch, consistent with the overproduction of early massive galaxies that has emerged as a recurring theme across Webb's early universe observations. The filaments themselves appear thinner, more tightly structured, and more clearly defined than many simulations reproduce for that period. One possibility is that the dark matter's behavior is slightly different from the purely cold, collisionless particle the standard model assumes, with some form of self-interaction or additional dynamics that sharpens the filament boundaries and concentrates matter in the nodes more efficiently. The other possibility is that some of the galaxies that should be distributed throughout the filaments migrated toward the nodes faster than the simulation's model, drawn by a combination of gravity and gas dynamics that the simulations underestimate. That migration would leave the filament interiors relatively depleted of large galaxies, while the nodes appear overpopulated. Both scenarios have different observational signatures that Webb will be able to distinguish with additional data. But while the Webb's nodes show more than expected, Webb has also found galaxies that appear to be forming in a location the entire framework of cosmic web theory says should be nearly empty. The cosmic web explains where galaxies form. Matter flows along dark matter filaments towards dense nodes, and galaxies grow at those nodes, fed by the continuous supply of infalling gas. A galaxy forming in the deep void, far from any filament, far from any significant concentration of dark matter, has no supply line. The model says it should not be able to grow. Webb found galaxies that appear to be doing exactly that. In several deep field surveys using Webb's near-infrared camera, astronomers identified compact, actively star-forming galaxies at early cosmic epochs that sit in regions where the projected galaxy density around them is low enough to suggest significant isolation. These objects are not clustered near obvious overdense nodes or along visible filamentary structures. They appear to be forming stars vigorously in locations that, under the standard model, should contain very little mass available for galaxy construction. The caveat here is observational. Webb is detecting galaxies, but mapping the dark matter underneath those galaxies requires inference from the galaxy distribution itself. An isolated galaxy might sit in a dark matter halo that is simply too low mass to have attracted visible neighbors yet. The filament connecting it to the larger cosmic web might be too low density to show up in current surveys. Some researchers interpret these isolated systems as early forming objects sitting in small, locally overdense regions that are the precursors of future cluster formation. Given enough time, they argue, the surrounding dark matter will accumulate further, neighboring galaxies will form, and what looks isolated today will eventually become the core of a larger structure. The model's timeline might simply mean we are catching these objects before their surroundings catch up. Other researchers are less comfortable with that explanation, particularly for the cases where the galaxy is not just isolated, but appears to have undergone substantial star formation that implies a significant gas supply with no obvious source in the surrounding environment. One proposal under active investigation is that certain regions of the early universe experience stronger than average density fluctuations in the dark matter distribution. Fluctuations too small to be captured in the statistical measurements of the early universe's radiation field, but large enough locally to seed isolated galaxy formation far from the main filament network. If real, those hidden density fluctuations would be a sign that the early universe's matter distribution was more complex and more varied on small scales than the smooth statistical description the standard model applies to it. That possibility, hidden small-scale structure in the early universe below current detection thresholds, points toward a deeper uncertainty. If the initial conditions of cosmic structure are more varied than the standard model captures, then every prediction the model makes about what we should find at different cosmic epochs carries an uncertainty that has never been fully quantified. And that uncertainty, when examined carefully, threads back into the most fundamental question this entire investigation has been building toward. The possibility that the Big Bang model itself, the framework in which all of Webb's observations are being interpreted, may require revision at a level deeper than any measurement correction can address. The Big Bang model is one of the most successful theories in the history of science. That sentence is true. The evidence supporting it is overwhelming, drawn from independent observations across every wavelength of light, every scale of cosmic structure, and every epoch of cosmic history. The existence of the cosmic background radiation, the observed abundance of hydrogen and helium matching predictions from the first 3 minutes of cosmic history, the expansion of the universe confirmed by galaxy redshifts in every direction. All of these independently confirm the basic picture. When scientists in this field talk about revising the Big Bang model, they are not talking about overturning any of that. What they are debating, seriously and with growing urgency, is whether the specific version of the model currently in use, with its particular values for the energy content of the universe, its specific description of dark matter, its model of the inflationary period that preceded the Big Bang's hot dense phase, accurately captures the universe Webb is revealing. The current standard model, called lambda CDM, encodes specific values for the cosmological constant, the dark energy term that drives accelerating expansion, for cold dark matter, for the initial spectrum of density fluctuations produced by inflation, and for the expansion rate of the universe. Those values were set by fitting the model to the best available data, before Webb. Webb is producing data the model was not built to accommodate, and the strain is visible in multiple places simultaneously. The overproduction of massive early galaxies challenges the model's galaxy formation component. The oversized early black holes challenge its black hole growth physics. The Hubble tension challenges its geometric description of cosmic expansion. The early chemical enrichment timeline challenges its stellar evolution assumptions. The isolated galaxies challenge its small-scale structure predictions. No single one of these challenges definitively breaks the model. Cosmologists have known about several of them for years and have been working on solutions within the framework. But the accumulation of tensions, each independently suggestive and collectively pointing in a consistent direction, is generating serious debate about whether the fixes can all be applied simultaneously. The specific debates happening at conferences and in journals right now center on several questions: whether the initial density fluctuations from inflation were exactly the scale invariant spectrum the simplest models predict, or whether they had additional features on small scales that could seed faster early structure formation, whether dark energy is truly a cosmological constant, unchanging across time, or whether it evolves and was stronger in the early universe, whether cold dark matter is accurately described by a single particle species behaving as assumed, or whether dark matter has additional interactions that change its behavior on galactic and subgalactic scales. Any one of these modifications would ripple through the model, changing predictions across multiple observables, potentially resolving some tensions while creating others. The scientific process of testing those modifications against Webb data is actively underway. What makes this moment historically significant is that Webb is providing data precise enough and deep enough to actually constrain these modifications, rather than just speculating about them. Previous generations of telescopes could identify the tensions. Webb is generating the data needed to choose between the proposed solutions. That process is ongoing. The answer is not yet known. But one specific proposal, one that would address the Hubble tension, the early galaxy problem and the early black hole problem, simultaneously, is gaining enough traction in the research community to deserve direct examination. It is the possibility that the universe is significantly older than the number currently engraved on every cosmology textbook. 13.8 billion years. That number has felt certain for long enough that it appears in science textbooks, museum displays, and popular science content everywhere without qualification. Webb is providing data that has caused a serious, peer-reviewed scientific conversation about whether that number is accurate. The age of the universe is derived from the expansion rate and the composition of the cosmos. If you know how fast the universe is expanding and what it contains, you can run the expansion backwards in time to find when everything was compressed into the initial state. Different expansion rates give different ages. A faster expansion means a younger universe. A slower expansion means an older one. The Hubble tension presents two expansion rates. The early universe measurement gives a slower rate and corresponds to an older universe. The nearby measurement gives a faster rate and corresponds to a younger one. The standard model adopts a compromise based on the full data set, arriving at 13.8 billion years. If the nearby measurement is wrong in the direction Webb's corrections suggest, the true expansion rate is slower, and the universe is older than the textbooks say. How much older is uncertain. Preliminary estimates from researchers working on the Hubble tension suggest the corrected expansion rate, if the remaining tension reflects a true physical discrepancy rather than a remaining measurement error, would push the universe's age closer to 14.5 or 15 billion years by some calculations. Those numbers remain contested and preliminary. No consensus figure exists. But a separate and more radical proposal entered the literature through a paper that attracted significant attention when it was published. A team of researchers, analyzing Webb's images of the most distant galaxies, observed that those galaxies appeared smoother, more regular, and more evolved than they should be if the universe were only 13.8 billion years old at their epoch. They proposed that the universe might be as old as 26 to 27 billion years if a specific modification to the standard model involving the behavior of light in an expanding universe with particular properties were correct. That proposal was controversial. The majority of cosmologists received it with significant skepticism, pointing out that the modification required involves assumptions not supported by independent evidence, and that the proposal creates its own tensions with other well-established observations. The authors acknowledged the preliminary nature of their claims. The proposal is mentioned here, not as a likely answer, but as an illustration of how far the scientific conversation has been pushed by Webb's data. Researchers who would never have entertained a universe twice the standard age are now writing papers testing that idea against observations. Because the anomalies in Webb's early universe images are real enough and consistent enough to motivate exploring the outer edges of theoretical space. The mainstream debate is more conservative, but equally significant. A universe aged 15 billion years instead of 13.8 would give those early massive galaxies roughly a billion additional years to form, which resolves some, but not all, of the galaxy formation tension. It gives early black holes more time to grow toward the masses Webb observes, reducing the tension with growth models. It relaxes the compressed timeline for chemical enrichment in the early universe. Every one of those resolutions is partial. The age shift alone does not solve all the problems. The remaining problems point toward a more fundamental issue in the model, one that a single numerical adjustment cannot fix, because it involves not the age of the universe, but the accuracy of our measurements of its density and geometry in the earliest moments. The early universe's measurement of the expansion rate the 67 figure that disagrees with the nearby measurement, comes from the cosmic background radiation. That radiation is the most precisely measured signal in all of cosmology. Its temperature pattern has been mapped across the entire sky with instruments sensitive enough to detect variations of 1 part in 100,000. The measurement itself is almost certainly correct. The question is what the measurement means. Interpreting the cosmic background radiation requires a model. The temperature ripples in that ancient light encode information about what the early universe contained, how dense it was, what fraction of its energy was in dark matter, what fraction in ordinary matter, and what fraction in radiation. Given those quantities and the laws of physics, the model predicts how the universe evolved from that early state to the present, including its current expansion rate. If any of those input quantities is slightly off, the predicted expansion rate shifts. The predicted age shifts. Every derived measurement shifts with it. One parameter that has attracted significant scrutiny in this context is the density of ordinary matter in the early universe. The cosmic background radiation constrains this density very tightly, and the value obtained is consistent with an independent measurement from a completely different source, the abundances of helium, deuterium, and lithium produced in the first 3 minutes of cosmic history, a process called Big Bang nucleosynthesis. Those abundances, measured in the oldest and most chemically primitive stars and gas clouds, match the density implied by the radiation. That agreement across independent methods is reassuring. But a third, more recent probe of early universe density has introduced a small, statistically suggestive tension. Surveys of how matter is distributed in the universe today, using the weak gravitational lensing of background galaxies by foreground matter, measure the clumping of matter across cosmic time. That clumping depends on both the initial density and on how dark energy and dark matter have influenced structure growth since. Several independent lensing surveys have produced a clumping measurement that is slightly lower than what the radiation-based model predicts. The discrepancy is called the sigma-8 tension. It is less famous than the Hubble tension, and its statistical significance is lower, but it exists independently and points in a consistent direction. The universe appears slightly smoother, slightly less clumped at large scales than the model predicts, given the early universe's measured density. Webb contributes to this investigation through its observations of galaxy cluster masses and galaxy distribution at different epochs. By observing how quickly galaxy clusters assembled across cosmic time, Webb is measuring the effective rate of structure growth in a way that can be compared against the model's predictions. Early results are consistent with the nearby lensing surveys in suggesting the growth rate is somewhat below what the standard model, calibrated to the early universe radiation, predicts. If both tensions, the Hubble tension and the sigma-8 tension, reflect the same underlying cause, that cause must modify both the expansion history and the growth of structure simultaneously. Very few physical mechanisms do both at once. One candidate is a modification to the nature of dark energy, allowing it to vary with time rather than remaining a fixed constant. Another is a modification to gravity itself on cosmological scales. Either modification would require rebuilding the standard model from a level deeper than any measurement correction addresses. And if either is confirmed by future Webb observations and independent tests, the consequences for our understanding of the universe, from its origin to its ultimate fate, and for every measurement of distance and age we have ever made, would be profound enough to constitute the most significant shift in cosmological understanding in decades. You might wonder why a disagreement about the universe's age or expansion rate should matter to anyone standing on Earth. The stars will be in the same positions tomorrow morning, regardless of whether the universe is 13.8 or 15 billion years old. Your life is unaffected by whether the Hubble constant is 67 or 73. The answer is not about immediate practical consequences. It is about the reliability of our understanding of reality itself, and about what revised cosmological maps reveal about where Earth sits in the universe's story. If the universe is older than 13.8 billion years, the timeline of everything changes. The first stars formed earlier in real time, and their deaths enriched the cosmos earlier. The first planets capable of hosting the chemistry that leads to life assembled earlier. The window of cosmic history, during which life could emerge and evolve, is longer than the standard model suggests. An older, more slowly expanding universe has had more time to develop structure, more time for complex chemistry to spread through the cosmos, more time for the conditions that produced life on Earth to emerge repeatedly across billions of other worlds. If the universe is structured differently than our models assume, specifically if dark matter behaves differently, or if dark energy is not constant, then the long-term future of the universe changes. The Standard Model's prediction is that accelerating expansion, driven by the cosmological constant, will eventually push all other galaxies beyond our observable horizon, leaving our galaxy in effective isolation. If dark energy evolves and weakens over time, that fate changes. If dark energy strengthens, the universe ends in a scenario called the Big Rip, where the accelerating expansion tears apart first galaxy clusters, then galaxies, then solar systems, then planets, then eventually matter itself. Webb's measurements of the expansion rate and the growth of structure will constrain which of these futures the universe is actually heading toward. The star maps Webb is breaking were not just catalogues of positions and distances. They were, cumulatively, humanity's best attempt to understand the universe's history, structure, and fate. Every galaxy distance told us something about when that galaxy formed and what conditions it formed under. Every measurement of the expansion rate told us something about the energy content of space itself. Every observation of the cosmic background radiation told us something about the first moments of time. Webb is not making those maps wrong in a way that discards everything. It is making them more precise, and in the process, revealing that the precision we had was insufficient to catch the systematic errors that compounded across the distance ladder, the tensions that accumulated across independent measurements, and the structures in the early universe that our models had not fully anticipated. The revision Webb is driving is the healthy mechanism of science working as designed. Data confronts theory, theory is adjusted, understanding deepens. The universe turns out to be stranger, more complex, and more interesting than the previous best model predicted. What remains is the question of where Webb points next. Which specific observations are already queued or underway that are designed to stress test the most fundamental remaining assumptions? And what the resolution of those tests will tell us about whether we are at the edge of a major revision in cosmology, or whether clever fixes within the existing framework will hold the Standard Model together. Webb has been operational for a fraction of its projected lifespan. The fuel required to maintain its position allows it to operate for at least 20 years. The science has already been transformative. What comes next is designed to be definitive. Several major observing programs are either underway or queued, each targeting a specific weakness in the current cosmological model, with enough precision to either close the debate or force a clear revision. The first priority is extending the Cepheid calibration sample. Webb's early measurements of crowding contamination in Cepheid observations were based on a limited number of galaxies used as calibration anchors. Teams are now observing Cepheids in a much larger sample of galaxies spanning a wider range of distances, environments, and galaxy types. The goal is to measure the full extent of the systematic error across the calibration chain, with enough statistical weight to determine whether the corrected expansion rate falls cleanly within range of the early universe measurement or remains stubbornly above it. That outcome will tell the field whether the Hubble tension survives a full Webb audit of the distance ladder. The second program focuses on gravitational lensing time delays. When a massive galaxy or cluster sits between us and a distant quasar, the gravitational field of the foreground mass bends the quasar's light along multiple paths. Each path has a different length, so the quasar's light arrives at different times along different paths. Measuring those time delays gives an independent route to the expansion rate that does not depend on Cepheids at all. Webb can measure the brightness variations of these lensed quasars with the precision needed to make this method competitive with the Cepheid approach. If gravitational lensing time delays produce a value closer to 73 or closer to 67, it will be a significant data point in the debate. A third major program is systematically surveying the stellar mass function of galaxies in the first billion years of cosmic history. The mass function, the count of how many galaxies of each mass exist at each epoch, is a direct test of structure formation physics. If the early universe contains too many massive galaxies compared to model predictions, quantifying that overproduction precisely will constrain which modifications to the model, different dark matter, different inflation, different feedback physics are required to explain it. Webb is also conducting a deliberate search for intermediate mass black holes, objects in the range of thousands to hundreds of thousands of solar masses, sitting between the stellar mass black holes from supernovae and the supermassive black holes at galaxy centers. Finding and characterizing this population will reveal whether there is a continuous growth channel from small seeds to supermassive objects, or whether a distinct direct collapse channel must exist to explain the most extreme early black holes. One program with particularly broad implications is a deep spectroscopic survey of the reionization era, targeting the emission and absorption signatures of hydrogen and helium in the intergalactic medium during the clearance of the cosmic fog. By mapping which regions ionized at which epochs, and correlating that with the underlying galaxy distribution, Webb can image. The survey will test whether the photon budget from early galaxies actually matches what was needed to reionize the universe. If the photon budget falls short, something is missing from the model of early galactic radiation, and the identity of that missing source would be a major discovery. Beyond those programs, Webb is already returning data from targets nobody planned for when the mission was designed. The universe has a habit of revealing its most interesting secrets in the gaps between what was predicted and what is observed. Webb is widening those gaps with every new data release. The star maps that organized human understanding of the cosmos for centuries were built with the tools available at each moment of history: naked eye, refractors, photographic plates, radio telescopes, Hubble. Each instrument revealed structure invisible to its predecessors, and each revelation required updating the maps. Webb is the latest and most powerful instrument in that chain, and it is doing what every great instrument before it did, showing us that the map was cruder than we realized, that the territory is stranger than the map predicted, and that the process of bringing the two into closer alignment is the most exciting work in science. We are not at the end of that work. We are, with Webb, at the beginning of a new phase of it, the phase where the questions are sharper, the data is richer, and the universe, patient and indifferent, waits to see if we are finally asking the right questions.